Hello again. This series of videos will cover week 9 and week 10, so it's not going to be that many videos because we have an exam at the end of week 10, but we are going to talk about substitution reactions and kind of how we can take what we've already learned about addition reactions and apply them to a new group of reactions, namely substitutions. So we're going to talk about two different types of reactions today. We're going to do SN2 and SN1. Now you'll remember SN2 we already briefly talked about back when we did acids and bases. And so SN2 should look somewhat familiar. You've seen this before. SN1 will also be familiar. There's only one step in the mechanism that we haven't seen before. So we'll talk about that and we'll make sense of these two. And then the next couple of videos after that are going to be kind of the little details and all the other parts of these mechanisms that we have to consider when we're trying to do substitution reactions. How do we make a substitution reaction work very well? What are the things that will make a substitution reaction prefer SN2 over SN1, and why would we want that? All that good kind of stuff. So we got a fair number of things to get through, but I think a lot of this will build very nicely on the addition reaction stuff that we've already talked about. So here we go. So I want to start with the SN2 reaction because, of course, that's one that we've already kind of talked about. So SN2 stands for, well, it doesn't matter what it stands for, but it stands for bimolecular nucleophilic substitution. An SN2 reaction, the important point about SN2 reactions is that it's a concerted mechanism. And we recall from our addition reactions that a concerted mechanism means that all bond making and breaking occur in a single step. So remember also that in concerted mechanisms, when we were doing additions, right, concerted mechanisms like hydroboration, dihydroxylation, hydrogenation, those kinds of things, tended to have very well-defined stereochemistry in their products, right? In the addition reactions, defined stereochemistry in products. In addition reactions, this meant that all of our concerted mechanisms ended up being syn addition. In substitution reactions, we'll see that that's not necessarily what happens because we're only making one sigma bond, we're not making two, so things will change a little bit there. Okay, so let's look at 2-bromobutane. And I'm going to react this with, I don't know, what should I react this with? Let's react this with just ethylamine. And so when we look at this, we're going to use our standard, how do we approach an organic reaction, right? The first thing we look for is where is our base? We always start from our base, and we know that our base is generally going to be lone pairs or pi bonds, right? So of course we have no pi bonds in either of these molecules, and the only lone pairs we have are on the bromine or on the nitrogen. And so now we have to decide which of these is going to be our acid and which of these is going to be our base. And how do we decide what makes a good acid or what makes a good base? Right? We look at their conjugates, right? And so if we think about what is the conjugate base of bromine, right? Br minus is a really nice stable conjugate base, right? So when we look at bromine like this, we can think Br minus is a stable conjugate base. And of course, that comes from the periodic trends, the periodic table trends, trends is a stable conjugate base, right? And so that means that this reaction, this carbon-bromine bond, is probably more likely to react as an acid, right? We have a nice stable conjugate base there. This is more likely to react as an acid. Nitrogen does not have a very stable base, right? So if we were to remove a hydrogen from here and create N minus, or have something else happen where we break a bond and create N minus as our kind of conjugate base, this would not be as stable as Br minus, right? So we can figure out that this is probably our acid and this is probably our base, right? You'll notice that anytime we really use nitrogen, it tends to react as a base. It has a nice lone pair here, right? And so it can react as the base. And the lone pair is where we're going to start our reaction. Okay, so where is this lone pair going to go? Well, it's going to go react with the acid, and we want to generate Br minus. And so the plan is, here's the plan. right? Base reacts with acid, reacts with acid to produce stable Br minus conjugate base. So how are we going to do that? Well, step one, we have to break this bromine away from the 2-bromobutane that's there. So one of the things we have to do is we have to break this carbon-bromine bond, put the electrons onto the bromine in order to generate the Br minus that is our kind of desired product here, our stable desired product. Now, if we just did that, that would leave this carbon, carbon 2, would be left with a shortage of electrons, right? If it loses those 2 electrons, this carbon is left with those. This is where our base comes in. So our base can come in and add electrons to that carbon. Now remember, we're not moving the electrons away from the nitrogen. The electrons, the nitrogen, and the whole compound are coming with those electrons over here to react. And so when we draw this out, what we're going to have is we're going to have this, but now our nitrogen is going to have everything kind of came along with that lone pair that made this sigma bond. So here we're making a sigma bond, and here we're breaking a sigma bond. This is very much like acid-base chemistry, right? You make a sigma bond, you break a sigma bond in a single step, and you get this thing out. Now this is a positive charge on the nitrogen, right? Because nitrogen has 4 bonds and no lone pairs. And so we would probably want to lose H+. We can use that trick again, and we can get to this compound as our final product. And notice that what we've done is we've added this group, our ethylamine, in place of the bromine, right? The substitution has occurred where the nitrogen has replaced the bromine in order to do that, right? So this is an SN2 reaction. Everything happens in a single step. We make the sigma bond, we break the bond in a single step. We lose this group. We call this group the leaving group because we're not very imaginative, and it's a group that leaves, and so we call it the leaving group, right? And the thing is, the leaving group is almost always a stable conjugate base, right? So the same rules that applied to stability of conjugate bases are going to apply to the stability of our leaving group once it has left. And so in this case, we get our final product here. This is our substitution SN2 product, right? Where the bromine has been replaced by nitrogen and the groups that are attached to that nitrogen. Okay, so SN2 is very straightforward. It's very much like an acid-base reaction, very much like the Bronsted-Lowry acid-base reactions, right? Where everything happens in a single step, we're producing conjugate bases, etc., etc. Now, it's a concerted mechanism, but the SN1 reaction is not, right? The SN1 reaction involves a carbocation. And so we're going to use a different set of rules to kind of talk about the SN1 reaction. Now remember, whenever we're making a carbocation, we want to make the most stable cation we can. And we remember the rules, right? Tertiary is more stable than secondary, is much, much more stable than primary, which doesn't really exist. And we can also consider resonance when talking about stabilizing carbocations. So let's do a simple one. Let's do 2-bromo-2-methylbutane, or 2-bromo-2-methylpropane this time, plus, we'll just use methanol in this case. And so again, we do the same analysis. Where's our acid? Where's our base? What is this going to look like, right? And I think it's pretty clear that this will still be the acid because again, we have this stable leaving group, this stable conjugate base, this Br minus, and this will be our base. Now with SN1 reactions, what happens is we form a carbocation first. And so this sigma bond breaks. So we break a sigma bond to make a tertiary cation. and you'll get a nice stable tertiary carbocation here. Now, once we make a tertiary carbocation, we immediately start to think about what can cations do. And so when we did additions, we said we have to watch out for rearrangement. Not a problem in this case because it's a tertiary cation, so it's not going to rearrange anywhere. And then we can either lose a hydrogen to create a pi bond, or we can have something come in, a base come in and react with that carbocation. And so that's what we get in this case, where we get the methanol coming in and adding to this. And we get a similar intermediate to what we've seen before, right? And now we just lose H plus, and we get our final substitution product. Now, once again, we're replacing the bromine with our base, in this case, OCH3. In an SN1 reaction, though, we have a different mechanism. We have two separate steps. So step 1 is to make the cation, and step 2 is for our base, or our nucleophile, right, to come in and react with that cation. Right, so this should remind you a lot of the addition under acidic conditions, right? So if we had H plus and methanol adding to an alkene, we would use the alkene to make the carbocation first, and then we'd have that carbocation be attacked by methanol or whatever our base is, right? So in this case, we're doing the same thing. We're just making the carbocation in a slightly different way. And so this is very much an addition reaction, or looks like an addition reaction mechanism, except for this very first step. And so if we have a good leaving group, this is still a leaving group, right? So we're still going to call this the, whoops, we're still going to call this the leaving group. This is still a stable conjugate base. Okay. But if we have a stable leaving group and we can make a stable cation, like a tertiary carbocation, we can make a cation and then have this come in and do this. Okay. So I'm going to stop this video here, but the question that obviously comes up now is why would we do SN1 or SN2? Like, what is the difference between these and when does one happen over the other? So that's what we're going to tackle in our next video. Stick around for that one.